Cool. So, yeah, after this introduction by Bas to what we do in general, I want to show you a project together with Danil that we did recently at Entrix, where we specifically use forecasting together with optimization to do exactly what Bas described, to balance renewables-powered electricity grid using batteries. What I want to talk a bit about is first the Entrix data science team, who we are and what we do in general, then a bit about grid-scale batteries to give you the context for this project, as well as which electricity markets exist and why there's actually not just one market, but there's many of them. This is also important context, then what the task actually is that we're solving in this project, and then Danil will give you the technical details that you're probably more interested in, how we actually forecast electricity prices, how we use them to maximize battery revenue, and also a bit about future directions for this. So just first about our data science team, we're currently 5 people, and we're planning to grow to 10 to 12 people by the end of the year. We have quite a mix of backgrounds: physics, mathematics, engineering, economics, and even architecture. And I think what's quite special about Entrix and Flexa is that the data science team is really at the core of the value proposition of the two companies. And yeah, I want to show a bit here why. Actually, when we asked ChatGPT to how a team like this could look like, this is what it came up with. So not sure what that means. All right, but so about grid-scale batteries, they are, I would say, still a relatively recent development, so maybe you haven't driven by one yet, but they're basically shipping containers full of battery cells that are put on some empty space of land and connected directly to the grid. And they're really just there to store energy and then release it back into the grid, depending on when that makes sense. And they can become really large now, kind of approaching the size of a large power plant. In terms of what's planned to be built in the next few years in Germany. And then another important, really basic thing about batteries is they have a power and they have an energy capacity. So power is about how much work the battery can power in an instant of time, and an energy is just power times time. So power is also the time derivative of energy. And a typical battery now has typically a duration of 2 hours. That means it can provide full power for 2 hours. That's an energy to power ratio of 2. That's quite common, and that will be important later. And now there are a lot of different electricity markets that we can serve with the battery. I won't explain every single one of them, and these are not even all of them. They're just the ones that are relevant for grid-scale batteries. And they are mainly divided into a wholesale market and frequency response markets. And wholesale markets are about shifting energy at longer time scales. Think about hours, maybe from shifting energy from the middle of the day when there's a lot of solar production to later in the evening when there's a lot of demand because people come home and start using their hob or the TV and so on. And frequency response markets are much shorter term. They're about reacting to short fluctuations in supply and demand at second level. To make this a bit more clear, in a really simplified way, this is how a day could look like on the grid. So you have supply peaking in the middle of the day when it's a sunny day and there's a lot of PV installed, like we actually have in Germany at this point. And then you have demand peaking later in the day, and actually in the middle of the day you have more supply than demand, and then in the evening you have way more demand than supply. And what you could do with the battery, very simply, charge it for 2 hours in the middle of the day. These are the 2 negative bars, and discharge it into the grid for 2 hours in the evening. And this would be kind of an action at 60-minute resolution. But actually what demand looks like is a bit more like this. So the previous curve was really smooth. So you also need to react to deviations within those 60 minutes. So not every single second in a 60-minute where we may be charging, there really is a shortfall of demand. So you might have to reverse your actions. And that's why we need to combine these different markets with each other. Also important is that these markets take place at different points in time. So we first have to bid into the frequency response markets in the morning. And then later in the day, we can start trading in the wholesale markets. And this timing difference is important because when we have to decide how much we go into the different frequency response markets, we are not actually the wholesale markets haven't opened yet, meaning we have to forecast what we think is going to happen in the wholesale market because this would be the alternative use case for the battery instead of frequency response. And when we want to think about how to mix these markets, we have to forecast what's going to happen later in the wholesale markets because we don't know that at the time when we have to bid into the frequency response markets. And then how do they, the different markets affect each other? There's a lot of rules that apply to the battery if you are in a certain market. So this is actually just to show that it is quite complicated because the one market applies an energy limit to the other markets or a power limit. And these are all, in the end, constraints that we have to take into account into our optimization. But basically, what you can maybe take away from this picture is it's about power and energy limits that come out of these different markets. And this results in this task for us essentially that you can split into two. The first is actually just a, as I've written there, relatively simple optimization problem. We want to maximize the revenue we get from the two frequency response markets, and that's just a linear term. The more we bid into the two frequency response markets, X1 and X2, the more we earn, and the slope is determined by the price of these two markets, which is the price of FCR and the price of AFR. These are the two names of the frequency response markets. But the revenue in the wholesale markets is then also determined by how much we have bid into the frequency response markets and also depends on other prices. And that's a function R that is quite complicated, depends on these previous constraints that I described that we then have to model and solve the optimization problem. So the first task essentially is to model this R and then solve the optimization problem. The second task is to forecast all of these prices because they won't be known at the time when we actually solve the optimization problem. So we are also building models for those 4 different prices. So basically, the optimization task and the forecasting task are separate but come together. And Danil will give more details about these two.
Hey. Thanks. Hopefully it will be as exciting as it sounded. So basically, this is our approach to the first task. There's a task of predicting prices. One being frequency response market, another one being the wholesale market. But as you can see, they actually quite correlated, even though they being cleared in slightly different time, because they both driven by the same drivers. They both driven by the expected renewable energy production, by the expected consumption by the large consumers, and so on. And by predicting those or just looking up those drivers, we can predict with our machine learning models how prices will develop during the day. Or the bottom example is also one interesting point. It's AFR capacity prices versus hydro pump storage available on the market. So hydro pump storage plants are one of the main players on the AFR capacity market. So, one of the main players on the AFR capacity market, and outages or plant maintenance on those power plants are actually way well planned in advance, and person can just Google where those outages are going to happen or when this maintenance is going to happen, and that helps us to predict prices. And there are dozens of such markers that help us to do it. And in the end, we built models, mostly it's XGBoost models. Microphone? Oh. Okay, thanks for letting me know. Yeah, so there are plenty of features ranging from weather data to just autocorrelative features. We trained the model on the recent data, starting from February of the previous year. And that is because markets are actually quite volatile, and those fundamental drivers change from time to time and quite drastically. So, for example, you can see the prices of AFR capacity market, how they change starting from 2023 to the beginning of the year 2025. And you can see that in the beginning of 2023, prices were quite high, and those high prices never happened again. And that indicates how fundamental relationships that drive those prices actually change, because even with the same fundamental data like the same weather and things like that, that prices never happened again, and basically model that has been trained on the data from 2023 will not work anymore in the year to 2025. Yeah.
How do you handle regime skins in that sense?
How do I handle what? Sorry?
Regime skins, like this you explained. So do you cut the old data and you don't consider anymore, or do you add, say, information that something happened?
Yeah, so the training data is usually not way more than half a year or so, because basically the fundamental relationships that your model will learn, they do not work anymore if you train on the data older than 1 year. Yeah, sorry.
What was the reason of these high prices in 2023?
Well, specifically those high prices were driven by the change of the market rules. So the way how market is cleared and what players are allowed to participate in this market have changed, and that actually changed the general market dynamics. And because more players got allowed after the middle of 2023, the prices dropped down and never raised up again, the highest they were.
Okay, so we will have time for questions at the end of the talk, because then I can hand over to you the microphone so that everybody can hear it.
All right. And the bottom plot just shows the change of the volatility in the IDC market, which is a wholesale market. That's the regular vanilla, so to say, energy market. And that indicates the higher involvement of the photovoltaic and wind energy into the system, because it's less predictable and prices just volatile more. And that's also one of the fundamental things that we need to predict, and that changes with time. And that pushes us into using more recent data instead of expanding our training window more. But on top of that, we have more difficulties. First of all, like Wolfgang said, clearing times of different markets are different. And for example, FCR clearing prices is a good predictor for AFRC prices, but because they happen just 1 hour apart from each other, the FCR clearing prices are not available by the time when you have to make a decision how much you want to bid on the AFRC. And that's how reality is. So fundamentally, this data is there because auction has been cleared, but data is just too slow to get to general public, and we cannot use it because of that. And that was the first part about prediction, and the second part is about optimization and placing ourselves on the market. So what this slide shows is the general, so to say, formulation of our optimization model, of our optimization problem. So X1 and X2 are our bids to the FCR and AFRC markets, which are frequency response market that we have to go into early in the day before continuous markets even open. And there's constraint. The main constraint that I wanted to draw your attention to is this one. So the total sum of all the bids that we place to the market cannot be more than the battery power, basically. So if your battery has, let's say, 10 megawatt of power, you cannot bid 5 to 3 markets. You should choose in which market, how much you commit. Because if you committed 5 megawatt to FCR, you cannot use this into any other market. And if prices turn out to be bad, then I guess you're screwed. Yeah, and that's how it works. Those pictures illustrate how this trade-off works in real life. So this is real-life data from one of our assets. The upper plot shows the evolution of state of charge of the battery, so how much energy battery has at what point of time during the day. And the lower plot shows the power that battery submits into the grid. So the bottom plot is basically just the first derivative of the upper plot. So when the power is positive, we discharge. When the power is negative, we charge. Or here it is vice versa. If it's negative, we discharge. So, and this is how unconstrained battery works. So when we can use any power battery has at any time, and we can be charged with any percentage at any time we want. But if we go into AFRC market, we constrain ourselves in terms of state of charge of the battery. So if we trade some volumes on AFRC market, we cannot be charged or discharged to any percentage we want. We impose some restrictions on ourselves, and that pushes us away from the optimal state of charge curve during the day, and that's basically the trade-off that you have on AFRC market. So you get paid for participating in AFRC, but you cannot do whatever you want on wholesale market anymore. And this is the trade-off in between those two markets. And for FCR market, it works other way around. It constrains you in terms of power. So if you are on FCR market, you cannot discharge and charge with whatever power you want, but you can discharge and charge to whatever percentage you want. And in reality, you have both, actually. And every day, based on prices that we predicted, we have to decide at what time, what constraints we want to impose on our state of charge of the battery, and what constraints we want to impose on our power of the battery. Yeah, but we are not done yet. So there are plenty of research that's going on in our company. We want to introduce more like probabilistic approaches, because for now, what I explained is based on the expectation value of prices, but also those expected values cannot realize with good probability. They actually within some distribution around it, and we want to take that into account. We want to also make some short-term forecasts to be more optimal on the continuous markets. Of course, there are works on MLOps side, so to update our models more frequently to monitor how they perform more accurately. And yeah, there are some works on reinforcement learning and stochastic optimization as well, to kind of explore other fields and other possibilities there. Yeah, that's it from our side. Thanks for your attention, and if you have questions.